We continue section 4.4, system coordinate systems. So we know that every vector from a vector space can be written as a linear combination of vectors from the basis, and those scalars are unique in regard to a basis. And the scalars are called the B coordinates, and we can put them into the vector. So we're gonna move on to page 105 that we just finished geometrical interpretation of the coordinates. And we are kind of halfway through the page. So to find the vector x with b coordinates that has 1 and 2, so those are the scalars c1, c2 related to the basis. That's my base. So b coordinates c1, c2 of x satisfy the equation. The vector x is equal to c1, b1 plus c2, b2. And if I substitute this, I have c1 times the base vector plus c2 times the base vector. We know that c1 and c2 are b coordinates. So this is my c1, that's why we substitute here. This is my c2, we substitute to this one. And I multiply this across, I'm gonna get the vector 5, 4, which is my vector x. So note that this equation, this is a vector equation. We can write this equation in the matrix form. If I put the first column minus 1, 2, the second column right here, then I can put the coordinates x1 and x2, because by the matrix vector multiplication would be column times the first coordinates, column times the second coordinates. So we put this matrix, we can call it, and it's called change of coordinates matrix from base to the standard basis, and it is denoted P with the subscript of B. Note that the columns of this matrix are vectors from the basis. Basis vectors are linearly independent, so that matrix is invertible. Yeah, that's exactly what it says here. Since the columns of P are vectors from the basis, so they are linearly independent, so the matrix is invertible. So what we have done there is the matrix times the coordinates vector, and is equal to the given vector. If we multiply both sides by the inverse of that matrix, then inverse and P is identity, so it disappears, and we have inverse times X. So this, the matrix P inverse of P converts X into its B coordinates, or XB, and matrix P converts X B coordinates into the standard coordinates, that is into the X. So because to find X, I have X, I need to multiply times the matrix P. So that's why P converts from the B coordinates to the standard. And if I have B coordinates and if I have the vector and I would like to find the B coordinates, I would multiply times the inverse. So that's why the inverse converts X into B coordinates. So then we have simple example. And that example says, given the basis and the vector, find the change of coordinates matrix B to the find the change of coordinates matrix from base B to the standard basis. So we're looking for the P matrix. So P matrix has columns of the P matrix are the vectors from the basis. So this is my first vector. Oh, here we should put it here. First vector, second vector, and to find the inverse, how do we find the inverse? Here's the formula on the side. So 1 over determinant, and then we're gonna swap the diagonal entries and minus the other one. So determinant would be 4 minus 2, which is 2. So it's gonna be 1/2 times, we swap those coordinates. So 4, and then we have minus 2. So the matrix, it becomes it becomes, once you perform the calculators, you should end up with the inverse matrix right here. But the coordinates matrix, so the matrix, what they ask me in part A is the matrix PB, which is just this matrix. And to find the B coordinates, we would use the formula. We would use the formula that XB is equal to P inverse times X. So that's what we have right here. XB is equal to P inverse times X. So we have the B coordinates that we're gonna use the inverse matrix times the column, and we multiply them times the vector X, we multiply them, and this is the B coordinates. And we can easily check, that. They check this C1B1 plus C2B2 is equal to X. And if you multiply, so 3 times the vector 1 minus 2 plus 0 times the vector minus 1, 4, that gives me the vector 3 and negative 6, which is my vector X. Next example, we have let the basis be let the basis be the polynomial basis, is the basis for P2. Find the coordinates vector of P relative to that basis B. So if I have vector P, I can write this as a linear combination of vectors from the basis. So I need to find the coordinates C1, C2, C3. So if you substitute that, this would be my C1 times the first vector from the basis, C1 times the first vector from the basis, plus C2 times the second vector from the basis, plus C3 times the fourth vector of the basis, and it's equal to the original vector. Perform the calculations, and you should end up with the C1, C2, C3 having 2, 6, and minus 1. So that would be my B coordinates. I would recommend pause the video and perform the calculations. Check with the notes. And last example from this section is example number 7. From the textbook, find the coordinates vector Bx of x relative to the given basis. So we have the given basis and the vector. So we know that the B coordinates vector are the scalars, is the vector with whose coordinates are the scalars. So C1 times B1 is equal to my vector x. So what we are doing, nothing else but solving the equation A times C. If you think that this vector C is C1, C2 is equal to x. So this vector who has coordinates vector who has vectors who has coordinates C1, C2, C3. Put to augmented matrix, perform the row operation, and you should end up with the scalars C1, C2. So this is my B coordinate vector.